So welcome to this. This is the Further Math Support Program online revision session for Edexcel S3, and in this session we're going to be looking at hypothesis testing for the mean and for the difference in the mean. And there's going to be a little bit of work about estimators in here as well, and how we use the central limit theorem. So quite a lot of links with confidence intervals as well. So what do we need to be able to do? Well, as I've said, we need to be able to perform a hypothesis test for a parameter mu of a normal distribution. Okay, so you'll be told that your distribution is normal, and you may be asked to perform a test based on what you believe the population parameter mu to be. If it's not a normal distribution, then we have to invoke this thing called the central limit theorem, which enables us to do the same sort of idea. Okay, and a lot of this is to do with how the distribution of the sample mean is formed. We also need to be able to hypothesis test for the difference between the means of two normal distributions of known variance, and that's quite critical because we need to know the variances to be able to assume that the difference between them is going to be normal as well. So it's quite an important thing. And we also need to be able to use the hypothesis testing for the difference between means using large samples. So if we're going to be using large samples, again, we're going to be invoking this thing called the central limit theorem. And also, if they are unknown variances, we're going to be using s squared instead of sigma squared. And in this particular case, because we're using the central limit theorem and we have unknown variances, we must have a large sample, much larger than normal. Otherwise, well, in fact, actually, your mean isn't normally distributed in this context. It's actually something called a t-distribution. But as your sample size increases, your distribution looks more and more normal. So it's just quite important to be aware of the subtle differences between number 3 and number 4. Okay. So this is a fun question for lots of people. Explain what you understand by the central limit theorem. So this is a pretty standalone question. It could be contextualized. So as I said in the video for confidence intervals, it may be explain the importance of the central limit theorem in this case. But this is quite a nice sort of standard question about stating what you understand. So we're going to have a large sample of size n, consisting of the following observations, all the way up to xn observations. Okay, and our central limit theorem states this. Okay, drawn from any distribution with a given mean, so we'll call it mu. So with a mean mu and a variance sigma squared. Okay, so far we've actually got 2 marks because you've understood that we need a large sample size, and we've understood that it comes from any distribution. And then what we can say is that x bar, now really it's approximately distributed. It isn't exactly distributed, but again we need to realize that it's approximate. But the sample means are distributed with mu sigma squared over n. Okay, so as I said in another presentation, sigma over root n is called your standard error. Okay, so that's what we're looking for. You get 1 mark for stating that we're dealing with large sample sizes. Whoops, sorry, B marks. You get another B mark for stating that it's from any distribution. Actually, it's not entirely true because it's not from a normal distribution, because you wouldn't need to use the central limit theorem. And also there's a distribution called Cauchy, which doesn't play ball either, but there we go. And then you get your final mark for stating your distribution approximation correctly. So it's one of those really sort of let's wake you up for an S3 exam type question, really. Okay, so June 2010, question 1. A report states that employees spend on average 80 minutes. So there's a key thing. Spends on average 80 minutes every working day on personal use of the internet. The company takes a random sample of 100 employees and finds that their mean personal internet use is 83. So we've got a belief, we've got a sample mean, we've got a sample level, and we're also given a sample standard deviation. Okay, so we are given an s squared here. You could use sigma squared, but really it's s squared. The company's managing director claims that his employees spend more time on average on personal use. and we're asked to test this at 5%. So again, with all of these things, it's about setting up the hypotheses correctly. So H0, we must use the population parameter, which is mu. Okay, got to use the population parameter. So mu, and the null hypothesis is everything is as we believe it to be, but the alternate hypothesis is looking at what we think. So we think that they spend more time on average, so that's going to indicate that mu has to be greater than 80. Okay, and again, it's got to be mu, got to be greater than 80. It's clearly a one-tailed test. Okay, and you get 2 marks. You get a B mark for each of those being correct. Okay, now the way of doing this is to standardize it. That's probably the most sensible way of doing this. So we are looking at a z value of x, I'll just write it down, so it's x bar minus mu over sigma on root n, and we're doing this because it is a sample level, and it's given to you in the formula booklet as well. So z bar is equal to 83 minus 80 over sigma, which is 15, over root n, which is 10. And if we calculate all of that, okay, we're going to get a value of 2, okay, which is quite nice. Okay, so you get 2 marks for this. Now, how these are working is, as long as you attempt to do some standardizing with those 3 numbers, you're going to get a mark. Okay, so that's quite nice. And then you get your accuracy mark for getting a value of 2. Now, to perform the test, again, we need a critical value. We're looking at 5%. So 5% creates a critical value of 1.6449. So we've got a critical value of 1.6449. So again, what I can say here is that my test statistic 2 is greater than my critical value. Okay, so your test statistic is greater than your critical value. This leads me to reject H0 because we are in what's called the critical region. Okay, so we are able to reject H0 in this case. So let me just show you where we get here. We get a B mark for using the correct value. Please do not round these. Okay, use the value as it comes from the table. Okay, just be aware of that. So we're going to reject H0. So 2 marks for these always. So 1 method mark for what you're actually going to do, and then your final accuracy mark comes from contextualization. So what I'm really looking for here is there is sufficient evidence to suggest that employees spend more time on average on personal use of the internet. And again, don't abbreviate this, just write it out in full. Okay, you shouldn't be pushed for time in an S3 exam, so make sure that you're doing those final marks. That separates your sort of students aiming for A stars and A's at these, is just this attention to detail. So that's quite a nice question, and there are other ways of doing it, but really that's the sort of bog standard way on S3 of doing these. Okay, so finally, June 2011 question 4. We've got a shop manager wants to find out if customers spend more money when music is played in the shop. Okay, the amount of money spent by a customer in shop is X pounds, a random sample of 80 customers who were shopping without music playing, and an independent, that's really important there, independent random sample of 60 who were shopping with music playing were surveyed, and the results are shown. Okay, and we're asked to work out x bar and s squared. Now the key thing is you need to realize that s squared is equal to sxx over n minus 1. Okay, because we're looking at the unbiased estimator of the variance, not the variance. Okay, and that's really, really quite critical that you are very, very aware of that. So here we go, let's work these out. So we know, as I say, that x bar is equal to the sum of x over n. So this is going to lead me to have 5320 over 80, which gives me 66.5. And you get 2 marks for that, which is quite nice. One for the method, one for the accuracy. So to work out s squared, I've already alluded that that's sxx over n minus 1, not n. So sxx, as we did on s1, is going to be the sum of x squared minus the sum of x all squared over n. So in this context, it's going to be 392,000 minus 5320 squared over 80, and that's going to give me an answer of 38220. So S squared is going to be that number divided by 79, and we really need to see the over 79 for this. Okay, otherwise you're not working it out and you get no marks. So if we work that out, that's going to give me 483.8 effectively. Okay, so you're going to get 3 marks. Method mark and accuracy mark for working it out, and then an accuracy mark at the end. Now again, if we don't see 79, you're probably not getting the method mark because it's the incorrect formula for working out S squared. Okay, so that M1 is really triggered by using the correct formula, i.e. a divisor of n minus 1. Okay, so we're then asked to test at 5% whether or not the mean money spent is greater when music is playing in the shop. So again, we need to start defining things in my view. So we're going to have let mu m be the mean with music, and we're going to have mu n be mean without music. Now, the way I personally prefer to do this is to state, well, if there is no difference, then they should equal each other. But I prefer to write it like this. And the reason is, sometimes you're not just looking for a difference in means, you might be looking for the fact that there is a certain value that you attribute to this. And actually setting it up in this way just makes a little bit more sense in those types of problems. So here, more money is spent when there's music playing, so I would expect that to be greater than 0. And again, the question might say test whether or not the mean money spent is more than £1 greater when music is playing in the shop, and that enables you to do this here. Okay, so we need to work out the test statistic. Now we're told this, which is quite nice, in the formula booklet. So we're told that Z is equal to, and the formula that's used is x bar minus y bar minus mu x minus mu y, all divided by the square root of sigma x squared over nx plus sigma y squared over ny. Now we need to put this into the correct context. As I say, that's what's given you in the formula booklet, but we need to use the correct context. So first of all, we exchange x for m and n for y, and also we assume the hypothesis. So if I assume the hypothesis, this is now going to have a value of 0. So really z is going to equal, so x bar minus y bar, we're really sort of looking at m bar minus n bar, if you wish, divided by, and it's going to be s m squared over nm plus s n squared over n because these are clearly going to be samples that we're dealing with. So applying this formula now, we're going to have 69.0 minus 66.5 all divided by the square root of, and I'll tell you how these are marked in a minute, 483, or your 483 if it's incorrect, 797 divided by 80 plus 446.44, extend the root, divided by 60. Now what I'm looking for here, you're going to get, as always, you're going to get a B1 for the hypotheses. You're then going to get an interesting combination of method marks. You get a method mark, a dependent method mark, and then an accuracy mark. So your first method mark is for ensuring that you're using the correct form. So for instance, if you transpose the 80 and the 60 over, okay, you will probably still get your method mark. If you do something like squaring it or square rooting it by accident, you will lose that method mark. Okay, so it's very important that you are able to set this thing up correctly. Anyway, if we calculate this, this is going to give me a value of 0.6807, and this would be your test statistic. Okay, so that's what we've got. Just write that again. So we've got a test stat of 0.6807. And what we're looking at is 5% one-tailed. So again, we're looking at 5% one-tailed, which is going to give me a critical value of 1.6449. So in this case, our test statistic is less than our critical value. So as with all of these tests, we do not reject H0. Okay, there is insufficient evidence to suggest that. So that's your standard fare, and then you contextualize it. So suggest that the mean money spent with music playing is greater than without. Okay, and again, as with these, you get M1, A1 for doing the comparisons. Okay, so it's very important. I'll just go back to that question a second. It's very important, let me just look at these, that you are able to deal with hypotheses in these ways. So if it says, as I said earlier, whether or not the mean money spent is £10 greater when music is playing, all you would do is you would change that to a 10, which would mean you would change this to a 10 and this to a 10, for instance. Okay, and you'd have a minus 10 on the end and a minus 10 on the end. So that's just a demonstration really of what could happen with these. So you just need an awareness about how to set up your hypotheses a bit more correctly. Okay, just get rid of all of those. So make sure you've practiced how these work, and make sure you're fully aware when you're finding S squared and when you're using sigma squared. So again, one of the key features of that question, okay, because you're not told, is there's nothing about the normal distribution here. So they could ask you about why the central limit theorem is appropriate, or whatever you're doing. So again, you're using the central limit theorem in some contexts to be able to work out your test statistic.